Good day, everyone. My name is Dr. C. Sendamarikannan, and today I'm going to talk about the sources of mechanical vibration. This presentation will cover key sources of vibration, including rotational imbalances, misalignment issues, structural resonance, external forces, and operational conditions. Let's identify the origins of machinery vibrations. The key sources include misalignment issues, rotational imbalances, structural resonance, external forces, and operational conditions. Misalignment between connected parts can cause vibration due to uneven loading and wear. For example, a misaligned coupling between motor and a pump can create lateral forces that generate vibration. In this slide, we are seeing about rotational imbalances. Imbalances in rotating components can lead to excessive vibrations affecting machinery performances. The next thing is structural resonances. Certain frequencies can cause structures to vibrate excessively, potentially leading to failure. External forces and impacts. External forces such as shocks or impacts can introduce vibrations in machinery operations. Operational conditions, factors like speed variations and load changes may generate mechanical vibrations. Imbalance is the main cause of mechanical breakdown in rotating machinery. This phenomena is due to the non-uniform distribution of rotational masses. Rotational imbalance arises when mass distribution in a rotating machinery is uneven, causing vibrations. A fan or motor with uneven blade can cause significant vibrations at higher speeds. In this slide, we are going to see sources of imbalance. Imbalance can be caused by various factors such as uneven accumulation of dust, erosion of pump impellers, lack of homogeneity in cast parts, rotor eccentricity, unequal distribution in electric motor rotors, bent rollers, especially in paper industry machines, missing weights, bent shafts, and eccentricity. Imbalance in rotating machinery can lead to a cascade of negative consequences, impacting both performance and longevity of the equipment. Let's dwell into some of the key issues. Firstly, increased wear on bearings. The vibrations stemming from imbalances act like a relentless pounding, leading to accelerated wear and tear on the bearings. This significantly reduces their lifespan and can lead to premature failure. Secondly, noise generation. Rotational imbalances often result in excessive and disruptive noises. This impacting productivity and potentially causing health issues for personnel. Finally, the most important thing is this reduces the operational lifespan of machineries. The cumulative effect of vibration, wear, and increased stresses take a toll on the machineries. Ultimately, this can drastically shorten its operational lifespan, leading to more frequent replacement and increased costs. In this slide, we will discuss the another critical issue in rotating machinery, misalignment. Misalignment occurs when the shafts of connected machinery are not aligned correctly. This seemingly small deviation can lead to significant problems, most notably excessive vibration. Consider this, a misaligned coupling between a motor and pump. This misalignment can create lateral forces, which in turn generate vibration. This vibration is not just a nuisance, it's a sign of serious stress on the machinery. In the next session, we will explore the different types of misalignments you may encounter, understanding This types is crucial for effective diagnosis and correction. Now, let's explore the specific types of misalignment you might encounter. We will cover two primary categories: parallel misalignment and angular misalignment. Parallel misalignment occurs when the shafts are indeed parallel, but they are not in line with each other. Imagine two train tracks running side by side, but one is slightly shifted forward or backward. This is analogous to parallel misalignment. Even though they are parallel, this offset can cause significant operational issues. Angular misalignment, on the other hand, happens when the center lines of the two shafts intersects at an angle. On the left, you see parallel misalignment. The shafts are parallel but offset. On the right, you see angular misalignment. Shafts intersect at an angle. Misaligned pulleys are a common example of both parallel and angular misalignment. As you can see in these diagrams, pulleys are not properly aligned, leading to either a parallel offset or an angular deviation of the belt. This can cause premature wear on the belt and pulleys, as well as introduce vibration and noises. In this slide, we will clarify the difference between shaft misalignment and bearing misalignment. These two distinct but often confused issues in rotating machinery. Shaft misalignment, as the name suggests, refers to the misalignment of the rotating shafts themselves. This typically occurs between coupled shaft like a motor and a pump. As you can see in this diagram, center lines of the two shafts are not aligned. They may be offset, that is parallel misalignment, or angular misalignment, or a combination of both. The red dots highlight the points of misalignments. This deviation forces the shafts to rotate in stressed condition, leading to vibration, excessive wear, and potential failure. Bearing misalignment, on the other hand, refers to the misalignment of the bearings that support the rotating shafts. This means bearing housing or the bearing itself is not properly oriented. In this diagram, you can see how the bearings are tilted or offset relative to the shaft. Again, the red dots emphasize the misalignment. This can cause uneven load distribution on the bearing, leading to premature wear, increased temperature, and ultimately bearing failure. Understanding structural resonance phenomena. Structural resonance occurs when external forces matches a structure's natural frequency and it amplifies the vibrations. An example is a bridge swaying and resonating with wind gusts with the frequencies aligned, risking the structural integrity and collapsing of this bridge. To mitigate potentially damaging effects of resonance, it's absolutely crucial to implement preventive measures right from the initial structural design space. Addressing resonance proactively is far more effective and economical than trying to fix problems after construction. One powerful tool is the use of damping techniques. Damping works by reducing vibrations and limiting the transfer of energy within the structure. This helps maintain stability and prevents the buildup of oscillations that characterize resonance. This graph illustrates the impact of damping. The horizontal axis represents driving frequency, while the vertical axis shows the amplitude of the forced vibration. As you can see, without any damping, the amplitude spikes dramatically at the resonance frequency. However, with increased damping, the amplitude at resonance is significantly reduced, demonstrating the effectiveness of damping in controlling vibrations. Another key approach is to strategically
modify the design of structural elements. By carefully tailoring these elements, we can shift the natural frequencies of the structure away from any unexpected external forces. This effectively avoids the conditions that lead to resonance, ultimately enhancing the safety and stability of the structure. Mechanical systems often operate in environments where they are subjected to various external forces and impacts. Understanding these forces and their effect is crucial for ensuring the reliability and stability of these systems. Mechanical systems can experience vibrations due to external forces from machinery or the environment. These forces can disrupt the system's equilibrium and lead to undesirable vibrations. Take for instance a hammer striking a surface. This seemingly simple action introduces vibrations that propagate throughout the system, potentially affecting the stability and performance of the system. Similarly, machinery operating on uneven ground can cause significant vibration disturbances. The irregularities of the surface induce oscillations in the systems which can lead to premature wear and tear or even structural damage. Analyzing these impact forces is paramount for designing effective vibration control solutions. A thorough understanding of the forces at play allows engineers to develop systems that can withstand or mitigate these effects. Various vibration control solutions are available, including isolators and dampers. Isolators work by decoupling the system from the source of vibration, while dampers dissipate energy to reduce the amplitude of oscillations, what we seen in the previous slide. These solutions play a critical role in minimizing the impact of external forces and ensuring the smooth and reliable operation of mechanical systems. Operational conditions and their effects on mechanical vibrations. Mechanical vibration isn't slowly determined by design of a system. Conditions under which a machine operates plays a significant role. This explore how various factors can influence vibration levels. Operational conditions, broadly defined, can significantly influence mechanical vibrations. This includes factors like load variations, speed changes. Variations in load can lead to increased tension and consequently amplify the vibrations. Imagine a conveyor belt carrying varying amounts of material. As the load changes, the tension on the belt fluctuates, resulting in vibrations. Similarly, changes in speed can directly impact vibration levels. Think of a fan running at different speeds. As the speed increases, the vibration often became more pronounced. Environmental conditions also contribute to vibration. Factors like temperature and humidity can affect the properties of materials as well as the lubricants, ultimately influencing equipment performance and vibration. In conclusion, understanding the influence of operational and environmental conditions is crucial for accurately assessing and managing mechanical vibration. By considering these factors, engineers can design more robust systems and implement effective vibration control strategies.